Heat loss. Grab yourself a cuppa and let's beat the chill. Now, if you remember from the book, 5 key aspects of a successful heat pump experience. Installation. We need a high-end, top-quality installation. We then need to commission that system correctly, maxing the efficiencies from our heat pump. We then need to hand it over to the customer in a way that the customer understands the operating principles of our heat pump. And then obviously we need to look after the heat pump. We need to maintain its longevity with proper servicing. But those 4 out of the 5 parts, even if they are conducted seamlessly, they are futile without a strong foundation base. And that base is design. So what exactly are we trying to achieve when it comes to heat pump design? Well, if you remember from the book, what we are trying to do is create a system design that can cope with the worst conditions that our heat pump will encounter. We call it the design indoor temperature as opposed to the design outdoor temperature. Now, our design indoor temperature is to create a comfortable environment within the home based on the room type and also the build year as well. Our design outdoor temperature is the worst average ambient temperature for your region. So what we are doing with our heat pump is we're designing it to be able to cope with the worst, but also be able to handle more favourable conditions as well. Now, in our heat pump design survey that we're about to undertake, what we want to achieve is that maximum efficiency when we are running at our lowest ambient temperature. Now, the example that we're going to move on to shortly is a heat loss calculation for a living room, a habitable space. So we are going to design it for the worst conditions. We then need to ascertain the power that that room needs, the energy it needs to get from that design outdoor temperature to our design indoor temperature. So if you look at the diagram behind me, what we will try to create is a comfortable environment in the home of, let's say, 21 degrees for a living room. And we want to be able to achieve that when it is the worst conditions outside, our design outdoor temperature. Now for Scotland, that is -5 degrees. So this gives us a baseline, something that we are going to design to. Now in reality, you could design a system for any type of temperature that you like, but we need some guidance, and that's outlined in the domestic heating design guide that we are going to utilise in our example. So if we want to get the house to 21 degrees when it's -5 degrees outside, we have got a differential in temperature. If you remember, we term it the delta T. In this example, our delta T from the -5 degrees outside to the 21 degrees inside is 26 degrees of a difference. So what our heat loss calculation will do, it will calculate the energy that we need when it's -5 degrees outside to maintain an indoor temperature that is comfortable and is 21 degrees. Because if you remember from the thermodynamics that we covered and in the video, we will always have movement of thermal energy. And when it's 21 degrees indoors and -5 outdoors, our thermal energy will move one way, from indoors to outdoors. And what our heat pump has to do is match that energy to maintain that indoor comfortable temperature. So design is absolutely fundamental. We don't want to oversize the system and we don't want to undersize the system. We want to hit that sweet spot. So let's look at our heat pump survey and calculate that energy loss for our living room. Okay, gang, so before we jump into our case study, let's have a bit of a recap and cover some of the previous aspects that are starting to make up our jigsaw. Now, we should already understand part of our heat loss survey because we've covered thermodynamics and movement of thermal energy. We've also covered U values, where they come from, and why they are absolutely essential when it comes to fabric heat losses. Because as we know, a property is made up of many different parts of building structure. Because fabric heat loss, as we recap, is a result of the surface area of the element that we are calculating, multiplied by the appropriate U value for that structure, and then multiplied by the delta T. So either the differential between the indoor temperature and our design outdoor temperature, or from one room to the next. Bear in mind, there will always be movement of energy where there is a difference in temperature. Yep, our area in square meters multiplied by our U value multiplied by the temperature differential, the delta T. We then have ventilation and infiltration losses. Slightly simpler to calculate. These are a result of the volume of the room this time multiplied by the number of air changes per hour, which we'll cover shortly. Again, multiplied by the delta T between indoors and outdoors, and then multiplied by 0.33, which is a constant. It is the specific heat capacity of air. So V is the volume, number of air changes, and the delta T. Now, when it comes to buildings within the UK, building standards have changed over time. Now, you can see from this table is an average heat loss in kilowatts for properties based on their type, and then also the build year, because building quality is improving decade after decade, particularly when it comes to effectiveness and efficiency. So for instance, I am in a semi-detached property, and in pre-1900s, we would be looking at an energy loss of 15.5 kilowatts. But in modern standards, that is down to just above 4 kilowatts, so a massive drop in energy demand. So let's jump into our case study. Now, in this example, we have got a 3-bedroom detached house. The floor plan, downstairs we have a lounge, entrance hallway, dining room, and a kitchen stroke breakfast room. That's the ground floor. And then the upper floor is 3 bedrooms, hence the reason it's a 3-bedroom house, a landing and single bathroom. So some of the details that we would need to ascertain to calculate and perform a proper, accurate heat loss estimation. Some of the details of the property. So geographical location is important. We have an EH postcode in this example, which is the capital of Scotland, sunny Edinburgh. The house type, as we've already covered, is detached. The construction date is important. The number of bedrooms are 3, and the occupants per bedroom are 1 person per bedroom. So as a heating surveyor, there are some fine details that we need to get about the building itself. So I've already done the donkey work for us. So the external walls are an outer layer of brick, then there is mineral wool insulation, 50mm thickness, followed by an internal construction of 125mm high performance rated block, and then we have 12.5mm plaster board that is attached to the block with plaster dabs. The internal walls are breeze block with plaster skim either side, and the ceiling heights are 2.4 metres high. The windows are PVC double glazed. The roof is tiled with a 30-degree angular pitch. There is sarkin and felt, 9.5mm plasterboard, and there is insulation in the loft between the trusses or the joists, and that is 100mm thick. So this is all things that our surveyor would need to ascertain as accurately as possible. The floors are 100mm insulation and they are suspended, so there's an airspace below the floor. The ceilings, as we said, is 2.4 metres high. There's 19mm sheet boarding as flooring for the upper floor with airspace between the joists, so there is no insulation between ground floor and upper floor. There's 9.5mm plasterboard with the heat flow being upward. The external door is solid. The internal doors are 2 metres by 0.6 wide. Thermal bridging allowance, guys, I've put in as non-applicable. We will cover the reason for this as we go. Now, our project for our case study is just going to be a singular room, and we are going to concentrate on the lounge. So it is 3 metres wide, so side to side. The ceiling height is 2.4 metres and it is 6 metres in length. There is a singular window at the rear of the property, or the front of the property, sorry, I should say, which is 2 metres wide by 1.2 metres high. There are 2 windows at the rear which are 0.5 metre wide, 0.5 metres, but again the same height as the front window, 1.2 metres. And then there are a set of French doors, PVC, which are 2 metres by 2 metres. So we've got just about all the information that we need to utilise a domestic heating design guide and calculate our energy loss. So we're sticking to the SIBSE Domestic Heating Design Guide purely because it's accessible for everyone. I know that there are software programs and heating design teams out there that can make things a lot easier, but this is really where the foundation of heating design was created. Now, in section 3 of the Domestic Heating Design Guide, there is a calculation spreadsheet. Now, it can look ever so daunting when you first are encountered with it. It's broken down into 5 stages, but one of the good things about those 5 stages, each of our boxes have codes in them. Now, those codes relate to a reference guide that I've extracted, that basically it tells you the information that's needed in that box. So it is pretty user-friendly once you get your head around it. So let's jump into it, stage 1. So stage 1 is really the job information. So box 1.1, we want the name of the room the worksheet is for. Box 1.2 is the job name that the worksheet is part of. Box 1.3, the page number of the worksheets. 1.4, how many pages are actually utilised for the job. So how many rooms basically we're going to calculate the energy loss for. So quite an easy stage. We've got box 1.1, we are going to calculate the energy loss for the lounge. The job would just be the customer's name or your own name. This is page number 1. And it would be page number 1 of 8 if we were doing each of the individual rooms, but for the sake of speed, we are just going to concentrate on the lounge. So stage 1, very easy, job done. Stage 2, box 2.1 is looking for the temperature that we are designing that room to be brought up to, i.e. our comfortable living temperature. So to gather that, we go to section 3, page 16, where we're encountered with table 3.6. Now, this table is for properties constructed pre-2006. Our house was constructed in 1998, so this table does become important. For modern houses, i.e. built after 2006, the design temperature for all of our habitable rooms is 21 degrees, with bathrooms and shower rooms being 22 degrees. But with this table, we've got a bit more variation. So for our lounge, we are looking at a target temperature of 21 degrees. Now, this is just the foundational guidance. Your customer may need a different temperature, be that for medical conditions or other reasons, or they might just like the house to be warm or slightly cooler. So we can manipulate these numbers. This is purely the base guide. So box 2.1 will be 21 degrees. Box 2.2 is our outdoor design temperature, so the lowest regional average temperature for our region. So to ascertain that, we are going to table 3.7. Now again, it's regional. So for our Edinburgh property, we are looking at an outdoor average temperature of -5 degrees. In some instances, it may get lower than that. This is a regional average. Again, baseline, we need something to base our design on. Box 2.3 is then the differential between those two values, i.e. our delta T between the design indoor and the design outdoor temperature. So that would be 26 degrees. How many degrees do we need to raise from -5 to 21? Box 2.4 is a ground reference temperature. So again, back to the same table on page 17, table 3.7. So our ground reference temperature for Scotland is the lowest average temperature of the ground in the winter. And that this time is a positive, it's 5.5 degrees Celsius. So box 2.4 is 5.5. Stage 2 in the bag. Now stage 3 is ventilation losses. So box 3.1, we need to ascertain how many air changes per hour will our room encounter. So again, as a guide, we use the table on page 18. So our rooms are broken into 3 categories, A, B and C, and that is when they are constructed. So as you can see down the bottom, category A is pre-2000, B is 2000 or later, and category C is after 2006, so modern building standards. Our house is 1998, so we will be category A, and for our lounge, we will be 1.5 air changes per hour. And that goes in box 3.1. We then need the dimensions of the room. So the length, the width, and the height. So if you remember from our case study, our living room was 6 meters long by 3 meters wide with a height of 2.4 meters. Box 3.5 is the amount of air heated per hour in cubic meters per hour. So to ascertain that, we take the figures from box 3.1, 3.2, 3.3 and 3.4 and basically multiply them together. So the 1.5 air changes multiplied by the 6, the 3 and the 2.4 gives us 64.8 cubic meters of air every hour that needs to be heated. Box 3.6 is then our air change factor, and that is the specific heat capacity of air, which is a constant 0.33. Box 3.7 is then our design temperature difference, which was the 26 degrees from box 2.3, the difference between our outdoor design temperature and our indoor. So 26 in there. And then if you remember, our our ventilation heat losses are our air change factor multiplied by the volume of the room, multiplied by the specific heat capacity, and then by the delta T. So we take 3.5 multiplied by 3.6 and 3.7, and it gives us a total ventilation and infiltration energy loss of 555.984. I am not rounding anything up. I want to keep it as accurate as possible. So already just through stage 3, we are looking just over half a kilowatt of energy required. Box 3.9 through to box 3.13 is about the number of open flues and chimneys, which would obviously increase those ventilation or the air movement. Now, we don't have a chimney in our case study, so we could either put a line through that section or just go through the motions. So 3.9 would be 0, then 0 for box 3.10. 3.11 would be our specific heat capacity, which is a 0.33. Box 3.12 is a design temperature difference, which is 26 degrees. But when we multiply box 310, 311 and 312 together, obviously with a 0 being in there, the total is going to be 0. So that's stage 1, 2 and 3 complete. Stage 4, box 4.1, is all about thermal bridging. Now, we mentioned earlier that this is non-applicable for our design. So thermal bridging is anything that can create, well, the clue's in the name, a bridge between the inside structure and the outside structure. So things, as you can see there, like wall ties that would bridge that gap. Lintels for structures could do that as well. It can be a difficult thing to determine and utilise. Now, the main complications with thermal bridging: the level of impact of thermal bridges depends strongly on the quality and the attention to detail of the actual construction, i.e. has it followed the plan to the letter. It's often proportional to the building's insulation levels, therefore where fabric heat losses are reduced, such as in new builds and ultra low energy buildings, the previously insignificant losses via thermal bridges do become very important. They're usually hidden within the construction and cannot be identified post-construction without the tools such as thermal imaging cameras. As such, it's recognised that thermal bridges should only be determined by an architect whose detailing must be provided before the design work continues. If we were going to utilise thermal bridging, as you can see there, it's based on the type of building that we have, and it gives an additional thermal transmittance in watts per meter squared per degree, i.e. we add this to the U values of our structure. Remember, when we covered U values, the lower the U value, the better. So if we add something to it, it's going to reduce the thermal resistance and drive our heat loss up. So it's really is important that if you are going to apply them, it's done accurately. Down the bottom is an example from the Domestic Heating Design Guide of what that would actually do to a property's U value. So you can see from the example there, our internal or our building has a U value of 0.53 watts per meter squared per degree. But if we add that 0.1 in this example to it, it raises it to 0.63, which would then become a multiple of our fabric heat loss, raising that thermal energy loss through that structure. But for our example, we are going to omit thermal bridging addition, so box 4.1 will be a 0. Okay, box 4.2, 4.3 and 4.4 is the dimensions of our external walls. So our external perimeter is 12 meters because we've got the side wall, which was 6 meters, and then the front and the back wall, which are also external. I've just added those three dimensions together to get a total length of 12 meters in box 4.2. The height is 2.4, so we take the perimeter, multiply it by the height, and it gives us an external wall area of 28.8. Now at this stage, we are going to leave the external walls because not all of our external walls are the same structure. we have windows, and we have French doors. So we move down to box 4.5. Our glazing, again, I have added the widths of our three windows together, and the reason I can do this is because they are all the same height. They were all 1.2 meters high. If there were different heights, we may need to do them separately, and we could use the boxes down further down that allow us to do other aspects. But for this example, adding the three window widths together, which gives us 3 meters, and 1.2 meters of height gives us an area for our windows of 3.6 square meters. Okay, the first U value that we have had to ascertain. Now, our windows were PVC double glazed. So box 4.8, in the absence of manufacturer's guidance, we will gauge the U value for the windows using the table on page 35 of the Domestic Heating Design Guide, which, as we can see there, gives us a U value of watts per meter squared Kelvin of 2.8. Now, just as an example, if you look just above that, our single glazed windows would have a U value of 4.8. So again, the lower the U value, the better the thermal resistance. So box 4.8 is our 2.8 U value. Box 4.9 is our temperature differential from box 2.3 inside to outside delta T, which again, if we remember, is 26 degrees. Now, we can now calculate the energy loss through our windows, because remember, fabric heat loss is the area multiplied by the U value multiplied by the delta T. So we take box 4.7, 4.8 and 4.9, multiply them together, and we have got a total energy loss through our windows of 262.08. We've then got our external doors. Now, if you remember, again, from the case study, we've got a set of French doors that had dimensions of 2 meters by 2 meters. If we multiply those together to get the area of our French doors in box 4.13, that gives us a square meterage of 4 meters. Now, the U value, if you can remember from the picture of our property, the external doors were PVC double glazed also, so the U value will be exactly the same as the windows, 2.8. The temperature differential, again, is going to be the same as the windows, indoors to outdoors design temperature differential, 26 degrees. We then take the 4 square meters, multiply it by the 2.8 and then by the 26 degrees to get a total energy loss in box 4.16 of 291.2 watts of energy loss. Now, box 4.17 is now asking us to take box 4.4 and subtract the figures from 4.13 and 4.4. That gives us a net external wall area of 21.2, and that is simply the 28.8 minus the 3.6 and minus the 4 square meters, because we've already dealt with those. We now want to deal with the external walls. We now need the U value for the external walls. And again, our case study had our outside walls being brick on the outside, mineral wool insulation, 125mm high performance rated block, and then 12.5mm plasterboard on plasterboard dabs. So page 30 of the Domestic Heating Design Guide. Our U value therefore is 0.35, because this description exactly matches our structural element. The 0.35 is due to the fact that our inner leaf thickness, the high performance block, is 125mm. If it was 100mm, the U value would be 0.38, higher. So our 4.35 goes into box 4.18. Box 4.19 is then again the temperature differential between indoors to outdoors, which, as we should know by now, is 26 degrees. So the energy loss through our external walls is box 4.17, 4.18 and 4.19 and multiplied together, which gives us a total for the external walls of 192.92. Now, the interesting thing is the area of our outside walls is over 20 square metres compared to our French doors, for example, which are 4 metres, so 5 times the area, and yet the energy loss is lower. It's all about insulation and efficiency. Windows are much less efficient at withstanding that thermal movement than our insulated walls with our high performance block. Okay, down to box 4.21, which is our ceiling area. So the dimensions of our ceiling are the same as the room, which is 6 metres long by 3 metres wide, which gives us a total net area of 18 square metres. Box 4.24 is if we have any roof glazing, but obviously with our living room, the rooms above it are bedrooms, so having roof glazing in would probably be a bit funky. So we can just scratch that line. Box 4.3 is the net area minus any area for roof glazing, which would be non-applicable, so we're still the full 18 metres squared. The U value, remember we've got 19mm sheet boarding on the upper level, then airspace between the joists, 9.5mm plasterboard with heat flow being upward. So to get the U value, we go to page 41 of the Domestic Heating Design Guide, and our U value is 1.73 because there is no insulation between the joists, between the upper and lower floor. So 1.73 in box 4.31. Box 4.32 is the temperature differential. Now, we've been utilising 26 degrees up till now, but this is not indoors to outdoors. It's from the living room to the rooms above. So to ascertain that, we need to know the design indoor temperature for the rooms above. And because again our property was built in 1998, our target design temperature for a bedroom is 18 degrees. So the temperature differential is not 26, it is 3 degrees between the 21 degrees living room temperature and the 18 degrees for our bedroom. Now think of it this way, when you come to doing your bedroom, that is a heat gain. So the total sum of the energy loss for our living room, instead of being added to the total, would be subtracted from the total for our bedroom because it is a heat gain. So to get the energy loss through the ceiling, we take our 18 square metres, multiply it by the U value and then the differential in temperature, and that gives us 93.42 watts. Okay, we've got our internal wall now, box 4x1 and 4x2, which is the length and then the height. 4x3 is the area of our internal wall, which is 6 multiplied by the 2.4, which gives us 14.4. The U value, again, for the appropriate structure, and our internal walls are breeze block with plaster either side. So that comes from page 33, and right in the middle there, our U value is 1.43 because we've got 13mm plaster, 100mm breeze block with 13mm plaster on the other side. Okay, the design temperature differential this time, again, it's an internal wall, so we are not going outside. We back on, or our internal wall backs onto both the hallway and the kitchen stroke breakfast room. Now, both of those design temperatures are 18 degrees, which is simple for us. It just means that the delta T between the living room and the hall and the kitchen is 3 degrees. Again, there's a temperature loss from the living room to those rooms. There would be a temperature gain for the hallway and the kitchen. Box 4x6, is our square meterage multiplied by the U value multiplied by the delta T, which gives us 61.776 watts, and again, nothing rounded up. Okay, we are soldering on. All we have left to do now is calculate the heat loss through the floor, because we've done the outside walls, we've done the windows, we've done the ceiling, and we've done the internal wall. It's just the floor that we have left. So right down the bottom, box 4.34. The dimensions, same as the ceiling, 6 meters by 3 meters, which means box 4.36, the square meterage, would be 6 multiplied by the 3, exactly the same as the floor, 18 square meters. Now the U value for the floor. U values for floors are probably the trickiest to ascertain from the tables. Now, we had 100 mil insulation, but it's all about the configuration of our floor as well. So we have 1, 2, 3 exterior walls, with wall B being longer than wall A, the longest out the 3. We then use the column down the left hand side, far left, to gauge the short length, i.e. dimension A. Now that's both the front and the back wall of our living room, which was 3 meters in length. So off the bat, we're looking at the top line here, but then dimension B, for that to be true, needs to be between 3 and 5 meters long. Ours is 6. So we would then use row number 2. This time we are 5 to 7 meters, which is exactly what we want. And then it's all about the insulation thickness, and we've got 100 mil of insulation, so we are looking at a U value of 0.24 watts per meter squared per degree. And that goes in box 4.37. Box 4.38 is the temperature differential. Now, this is one that a lot of my trainees get tripped up on as well, and it's quite an easy thing to become tripped up on. We are not going from indoors to outdoors. We are transferring from indoors to the ground. Remember, it's the ground floor. So our target delta T will be the 21 degrees indoors, and the differential between the ground temperature, which from stage 2 was 5.5 degrees. So therefore, our temperature differential is 15.5 degrees. We then take the 18 square meters, multiply it by 0.24, and then by the 15.5 delta T, and that gives us an energy loss through the floor of 66.96 watts. So stage 5 is just putting all of the pieces together. So box 5.1 is the sum of all of the values in the far right column, including our ventilation losses from stage 3. That gives us a total energy loss for our living room of 1524.34 watts. So if we move that down to box 5.9, the last thing that we want to calculate, and it's an important factor when it comes to low temperature heating design and upsize factors for energy losses, is the watts per meter squared, the amount of watts that are lost for every square meter of floor space. So we take the 1524 and divide it by the 18 square meters, and that gives us 84.69 watts per square meter. As I said, it will be an important factor for following videos. So we've now successfully calculated the energy required for our living room. It's now up to us to take that energy loss in watts and then select the correct emitter that can match that energy. Much like our heat pump, with our emitter, our radiator, we don't want to oversize it and we don't want to undersize it. We want to get as close to that energy output as we can. And when we go back to the book, we'll size up that radiator.